Hi, Seth here. Welcome to the channel. TensorRT has been released for ComfyUI, which gives you real-time performance improvements on image generation. Starting with Stable Diffusion 1.5 and using Realistic Vision version 6, it takes about 68 seconds to generate the image with upscale. TensorRT gives a 26% performance boost. Doing a batch of 4 saves 20 minutes and 50 seconds approximately per 100 images. The benefit increases when moving on to SDXL. With a batch of 1 using latent upscale and face detailer, TensorRT is about 28% faster. With a batch of 4, it still manages to give a 26% faster generation. SDXL Turbo, on the other hand, offers the least performance increase and saves only 11 minutes per 100 images. Going for a batch of 4 in Turbo is even worse at a 14% improvement only. Stable Video Diffusion gets up to a 29% performance boost in the 14-frame model. The XT version 1.1 model, which is for 25 frames, you can save 20 minutes for every 100 video generations. Finally, Stable Diffusion 3 has the most performance improvements with TensorRT. It is up to 32% faster and saves over 1 hour and 20 minutes per 100 images. I will explain how TensorRT actually works. I also use a comprehensive workflow to build the TensorRT engine files. The workflow includes Boolean and logic nodes. Let me show you step by step how to create such a workflow and the benefits and current limitations of TensorRT in ComfyUI. Firstly, I would like to thank all the paid channel members for their continued support. I know the intro stats were a bit fast. You get 25 to 30% faster generations in SDXL, Stable Video, and SD3. Well, practical usage of local SD3 is temporarily out of the question, but still. For the performance benchmark, I tested the system in live workflows. Accurate measures come from real-life environments. All the test benchmarks given were on the second run, as on the first run, you have the base model loading, which takes about 5 seconds. TensorRT is an official custom node in ComfyUI that will work on all nVidia RTX tagged cards. Basically, when you train an engine for a 4090, that engine won't work for a 3090. TensorRT may be compatible with server-grade GPUs like the A6000, but I don't have the hardware to test it. I have no idea if it would work on an H100 system or the exact range of server-grade GPUs it is compatible with. I would share all the engine models I made for a 4090 GPU and the engine build and test workflow JSON files with paid channel members. However, you can just watch the relevant parts of the tutorial and create the workflow yourself, as I always show the entire workflow build in every video. The use of TensorRT is obvious for any business environment and deployment. Each second saved on system resources is money. Let's first understand how TensorRT works in ComfyUI. You have your Stable Diffusion checkpoint. At the time of this video, only these models and models fine-tuned over them are supported. I tested Stable Video 3D, Cascade, and CosXL, and they are not supported. Then, you have the TensorRT conversion node. This node's primary job is to generate the compatible model into a .engine file, which runs faster on the nVidia GPU. However, it is not a straightforward process. First, it needs to understand the parameters. These parameters would include the width, height, batch size, and frames per second if you are doing video. This ensures the engine is defined to compute according to these parameters only. These parameters should also match your checkpoint. Now, you can define them as a fixed, static, absolute number or give them a range. So, the TensorRT node now has the model and defined parameters. However, there is a problem. It cannot comprehend the underlying concepts or the meaning behind the model's architecture. TensorRT works with a specific representation of the model called ONNX, which stands for Open Neural Network Exchange. ONNX is an open format for representing machine learning models, essentially providing a common language that different frameworks and tools can understand. The conversion node converts all this to an ONNX format. ONNX here acts like a bridge between the model and TensorRT. The TensorRT now takes the ONNX model and analyzes its computational graph, that is, the sequence of operations that define the model. Now, it carries out various optimizations on the model. One of them is precision calibration. Quantization includes converting weights and activations from high-precision floating point, like FP32, to lower precision formats, like FP16 or even integer 8. When converting, it aims to minimize accuracy loss while maximizing the performance benefits of lower precision. TensorRT can also utilize multiple precision levels within a model to balance accuracy and performance. It does these automatically. So, the whole point of precision calibration is to speed up processing and reduce the computational load without significantly compromising accuracy. Graph optimization simply means analyzing and transforming the computational graph of the model to make it more suitable for execution on the target hardware. To repeat, a computational graph is the sequence of operations that defines the model. TensorRT combines multiple operations in the model's computational graph into single, more efficient operations. This results in faster inference times, reduced memory usage, and improved overall performance. Layer fusion includes vertical and horizontal fusion. Vertical fusion combines consecutive operations in a neural network into a single operation to reduce overhead and improve performance. The Stable Diffusion U-Net architecture has multiple instances of ResNet blocks, each consisting of convolution, normalization, and activation layers. These blocks can be fused together to improve performance significantly. ResNet blocks are the building blocks of residual networks, a type of deep neural network architecture that has been highly successful in image recognition tasks. The U-Net architecture used in Stable Diffusion incorporates ResNet blocks in both the encoder and decoder parts. Convolution layers extract image features, and normalization layers stabilize training. Rectified linear unit activation functions introduce nonlinearity. This means they transform the linear output of these layers into a nonlinear form by setting all negative values to 0. This is important because real-world data is rarely linear, and introducing nonlinearity allows the model to learn more complex relationships within the image data, improving the quality and accuracy of generated images. Parallelism refers to the ability to perform multiple tasks or operations simultaneously. Horizontal fusion combines parallel operations in a neural network into a single wider operation to increase parallelism and speed up computation. It can potentially be applied to certain parts of the Stable Diffusion U-Net, but its impact might be limited compared to other optimization techniques. Tensor fusion includes concatenation and element-wise fusion. Concatenation fusion combines feature maps from different levels for better image details. Feature maps refer to intermediate outputs produced by different layers within the network. Element-wise fusion, on the other hand, streamlines operations within ResNet blocks for improved efficiency. Batch optimization allows for the simultaneous processing of multiple images, increasing throughput. Shape optimization enables the efficient handling of various image resolutions and aspect ratios without needing separate model versions. Overall, graph optimization streamlines the model's computational process, resulting in faster and more efficient image generation in Stable Diffusion. TensorRT also efficiently manages the GPU VRAM. Instead of pre-allocating a fixed amount of memory, TensorRT dynamically adjusts the allocation based on the actual size of the image resolution and batch size. This ensures that memory is not wasted on unnecessary allocations for smaller images or batches. It also reuses memory locations no longer needed by previous operations to store the results of new operations. This minimizes memory fragmentation and reduces the model's overall memory footprint. Overall, dynamic tensor memory in TensorRT optimizes GPU memory usage for efficient image generation with Stable Diffusion, preventing memory wastage and enabling handling of various input sizes. Kernels are small programs that perform specific operations like convolutions or matrix multiplications on the GPU. A heuristic search is an intelligent search strategy that systematically explores different kernel combinations to find efficient ones. It doesn't try every possibility, but it uses clever algorithms to narrow down the search space and find good solutions quickly. Even with a heuristic search, the first solution is not guaranteed to be the best. Performance profiling involves running the model with different kernel combinations on sample input data and measuring their performance metrics like execution time and memory usage. Based on the performance profiling results, TensorRT selects the kernel combination that performs the best according to specific criteria, such as the fastest execution time and lowest memory usage. In short, kernel auto-tuning in TensorRT automatically selects the best algorithm for each operation in the model to optimize performance on the specific GPU hardware. Finally, the TensorRT node generates the .engine file, a binary file containing the model's optimized execution plan. The Load TensorRT node in ComfyUI will load the optimized engine file, bypassing the need for the original model checkpoint. Ensure the parameters used to build the engine file are consistent with your workflow settings. This will drastically speed up image or video generation, as the engine file contains a streamlined, hardware-specific version of your model optimized by TensorRT. Please note that the SDUNet architecture applies only to SD 1.5 and 2.1 versions. SDXL and Stable Diffusion are not pure UNet models. They are built on the UNet with a more complex architecture. Stable Diffusion incorporates attention mechanisms to capture temporal dependencies between frames in a video and continuous time steps for better video generation quality. SD3, on the other hand, is also not a pure UNet model and employs a modified version called a multimodal diffusion transformer. It incorporates transformer layers, is designed to handle multiple modalities, and combines the diffusion transformer architecture with flow matching techniques. Although the core TensorRT optimization principle remains the same, the optimization techniques may vary depending on the model. To summarize and simplify things, let's take the analogy of building a house. You start with a detailed house blueprint, representing the original Stable Diffusion model. Materials and specifications include the dimensions, number of rooms, and materials that will be used to build the house. In the model, these are parameters like image resolution, batch size, and precision. TensorRT conversion node is like a translator. This tool simplifies the blueprint into a format that the architect, TensorRT, can easily understand. The Onyx conversion is like a condensed version of the original blueprint, making it easier for the architect to analyze and optimize. The architect examines the simplified blueprint and figures out ways to optimize the construction process. The architect creates a new, improved plan that makes the construction process faster and more efficient. TensorRT Load Engine node is like a construction supervisor who guides the construction team using the optimized plan to build the house. The ComfyUI workflow is the construction site where the actual building process takes place, following the optimized plan. The final result is a finished house, built faster and more efficiently, just like the optimized model produces images and videos faster. The architect uses 4 key optimization processes during the building of the house. Appropriate materials are used for each part of the house to balance quality and cost, similar to optimizing model precision. Then, the architect streamlines the construction by finding more efficient ways to build the house, like combining steps or using prefabricated parts, similar to optimizing the model's computational graph. Managing resources efficiently on the construction site to avoid waste is similar to how TensorRT optimizes memory usage during model execution. The architect then chooses the best tools for each construction task, such as selecting the optimal algorithms for the model's operations. This behind-the-scenes process illustrates how TensorRT transforms Stable Diffusion models for faster generation in ComfyUI. However, it comes with certain limitations. ControlNet and LoRa's are not supported when recording this tutorial. I could cheese in the LoRa and make it work with some limitations. I had some issues with face detailer. Single large faces were not a problem. However, when using it on an image with many small faces, it generates some black images. I guess those image sizes were beyond the scope defined in the parameters. For Stable Diffusion, I can generate full HD videos on the 4090. But the training failed when using HD resolution to generate the engine for SVD. It generates images when using IP adapter, but it doesn't work. It's like the IP adapter is ignored completely. Similarly, it doesn't work with Google Style Align or when I apply the Focus and Painting patch. This is the workflow that I personally use to build the Tensor Engine files. I prefer this rather than entering the settings every time for each checkpoint. The workflow comes with a control panel, which allows me to configure the resolution, batch, and FPS settings, and I can easily switch between the predefined settings. I am using Boolean and logic nodes to automate the workflow. The workflow requires custom nodes, starting with the TensorRT node and the impact pack. I am using the logic and Boolean nodes from WasNode Suite. ComfyUI Studio for a couple of text nodes. Comfy math nodes are used extensively for the resolution calculations. Lastly, the RG3 nodes help build the control panel and organize the workflow. Add a load checkpoint and a load LoRa node. Connect them, and for now, set the LoRa node to bypass. TensorRT has a static and dynamic node. First, add the static one. Connect the model. So, with these two nodes alone, you can generate and convert any compatible model with static parameters. However, I will automate the workflow, allowing me to use static or dynamic with any model checkpoint I want without repeatedly changing the settings. Ensure you do not change the folder name TensorRT, as the load node will load it from this folder. In static, everything is fixed. This means that when you train any model, you must use these settings only, otherwise, it will give you an error. OPT here stands for optimal. Context means the token size. The optimal context value should always be 1. Keep the number of video frames at 0 for non-stable video diffusion checkpoints. For SVD, there are only two options here, 14 or 25 frames, depending on the SVD model. SVD checkpoints can only be optimized using static nodes. You cannot latent upscale when using a static node for an image checkpoint. For example, suppose you input an optimal width and height as 1024. When you latent upscale 1.5x, the model needs to generate the image at 1536 resolution, resulting in an error as the model is not optimized for it. You can also train the same model for 1536 resolutions and load it between the workflows. This is not advisable because the time it takes to switch between the models will result in a loss rather than a gain. The solution here would be to use a dynamic range, which a single model can handle. So why use static at all? Well, it's ideal for scenarios where the input parameters are fixed and known beforehand. This is common in production environments where consistent and predictable performance is critical. Generating a static engine requires less VRAM than a dynamic one. And since the engine is pre-built, there's no overhead during runtime for optimization. Convert all widgets to inputs except for context optimal. We are going to organize the workflow as we go along. Make a group and rename it to checkpoint and LoRa. Add two math integers to the number nodes. One would be for the width and the other for the height. Search and add a number input switch node. This node has a logic Boolean input that would output the desired resolution. Make the connections and rename the nodes to A and B for simplicity. Connect this to a display integer node from RG3. Rename this to static width. I will disable all nodes except these to test the Boolean logic. Add a logic Boolean primitive node. This is from the WasNode Suite as well. What this does is when the Boolean is false, the output will be B. And when it's true, it will output A. With this, I can control the width output. Rename the logic node to 512. I have taken 512 and 768 because I am first creating this for SD 1.5 checkpoints. Duplicate these two nodes for the height control. Also, duplicate the primitive logic node and rename it to 768. Make the connection and rename the static width to static height. If I set the second node to false, I should get the height as 768. We can have only 3 resolution combinations for SD 1.5 and static. That's square, portrait, or landscape. Duplicate the node and group it. Rename the group to square. Add 2 any switch nodes from RG3 and connect them with the Boolean input. Now connect the square group nodes with any 0-1 inputs. For the square node, both the Boolean should be set to true to get a 512 into 512 output. So you can see where I am going with this. Create 2 more groups. One would be for landscape, and one would be for portrait. The any switch node works by passing through any active input as output based on the number it is connected to. This means that if any 02 and any 01 are active, only any 01 will pass through. For any 02 to pass through, there should be no input for any 01. This is why we are creating groups. At any given stage, only one group can be active. Make the connection for portrait and ensure that the 768 Boolean should be false. Now duplicate, group, and connect again for the landscape. Ensure that the Boolean logic for the landscape is reversed. Now add a fast muter group node from RG3. Rename the group to SD 1.5 ratio. Go to the Properties panel and change the toggle restriction to max 1. This ensures that all groups can be turned off, but only one can remain active at a time. Type in the match title as shown. Let's check if the output is correct. Connect the width and height outputs to the static TensorRT node. Group these nodes and rename the group to SD 1.5. Let's add static SDXL resolutions to the workflow. Duplicate the RG3 any switch node and connect it between the SD 1.5 and the tensor node. Add the SDXL resolution node from ComfyMath. Convert the resolution to input and connect it with a primitive node. Rename the primitive node for clarity. Connect the resolution with the switch. Move the primitive node and create a group called SDXL SD3 static. Copy the static height and width and connect them with the switch as shown. I need to test the values as I go along. Club these nodes into a group called TensorRT Control Center. Duplicate the fast muter node, rename it to model, and change the match title to include SD 1.5 and the SDXL and SD3 groups. Now move the final width and height display integer nodes in the command center for easy testing. When turning on SD 1.5, ensure that the ratio is also on. When you switch to SDXL or SD3, it will take the values from the static resolution. Let's organize the engine file name as well. Add two CR text nodes from ComfyUI Studio. The first one would be the folder, so put TensorRT in small letters, one word. The second one is the engine file name, and you only have to edit this one. Add a CR text concatenate node and connect both. Put a / as a separator. Rename as necessary and connect it with the static tensor input. Group and organize the nodes. You can connect a display integer to test the output. Let's add nodes for Stable Video Diffusion. SVD is a bit tricky because we need to factor in that the frames value should be 0 when SVD is not enabled. However, when enabled, the value should be either 25 or 14 frames. Add two integer to number nodes. The first one will be the width, and the second one, the height. The width will always be 1024, and the height 576. Any other values for SVD don't work with TensorRT. Add two number to integer nodes, and connect them with the final switch. Group these nodes and name it SVD. Now, add a number input switch node and connect it with the static TensorRT node. Then, add another integer to the number node and connect it with A. The value for this node will always be 0. We need this value when not using SVD. Duplicate this node twice, one for 25 frames and the other for 14 frames. Add both nodes to two separate groups and name one 0/25 frames and the other 0/14 frames. Add another display integer here and rename it to frames output. Connect the 25 and 14 frames to an any switch node. This will further connect to number B. For the Boolean, add and connect a logic NOT node. Simply put, the NOT gate acts as an inversion node, meaning it does the reverse of the previously shown Boolean logic. To demonstrate, let me duplicate the integer to number and change the value to 25. Now, when the Boolean is false, I get the number A value, which is 0, and 25 when it's true. Convert the Boolean widget in the node to input. Now add an if none node from the impact pack. If I connect any input to this node, then when there is an absence of value, it triggers a false Boolean, which means output should be 0. Here the any input would be any output from the SVD group. So when the SVD group is disabled, I should get 0, otherwise, I will get whatever the input is defined for number B. Let's add the SVD group to the fast muter node. Turn off SVD and test. Okay, that works. Let's turn it back on and reconnect the frame switch to number B. Organize these nodes into a group and name it frames. Duplicate the ratio fast group node and include the 25 and 14 frames group. Let's test it. This error is because one of the frames, either 25 or 14, has to always be enabled as they are connected with the number B input. Go to the node properties and change toggle restriction from max 1 to always 1. If you enable any group other than SVD or disable SVD, the frame's output will always be 0. Rename and recolor the frame nodes. Delete the test display integers, then create a group for the static TensorRT node and the final switch. Name the group as static. The static part of the workflow is now complete. Add a dynamic TensorRT node. For dynamic TensorRT, choose a minimum and maximum range. The optimal value should be somewhere in between or closest to 1024 when doing SDXL SD3. The height and width should be the same for each group, that is, minimum should have the same height and width. The same goes for maximum and optimal. Convert everything to input except batch size and context. Do width followed by the height in the order of minimum, optimal, and maximum. Connect the model from the bypassed LoRa output. Frames from the frames group and file name prefix from the file name group. Add 3 any switch nodes. The first one connects to both minimums, the second to optimals, and the third to maximums. First, I am going to add the dynamic resolution for SD 1.5. Add 2 number to integer nodes. The dynamic resolution is pretty much fixed and standard for non-SDXL. Duplicate the display integer and connect with the width output. Rename it to minimum. Duplicate again and connect this with the height. This would be the optimal value. Duplicate once more and rename to maximum. Add an integer binary operation node and rename it to 2x multiply. This gives me the flexibility to latent upscale by 2x. Change the operation mode to multiply, then convert the A widget to input. Make the connection and change the value of B to 2. Keeping the dynamic tensor node disabled, test it. The minimum should be 512, optimal at 768, and maximum at 1536. Connect to each of the switch nodes as shown. For the SDXL, SD3 dynamic values, copy and duplicate these nodes. Arrange the nodes and group them as shown. To get the maximum SDXL, SD3 range, choose a minimum supported width like 640. The maximum is 1536 if you are going to upscale to 3K. However, I usually don't upscale more than 2304 by 2304, so I will choose 1152 as the B value. Connect these values as well with the dynamic switches. If you are a bit low on VRAM, you can choose a shorter range. For me, it's preferable to have 2 range sets, depending on the use case. Just replicate these nodes and put in the desired range, and group it under SDXL, SD3 medium, or short range. Connect these values as well with the dynamic switches, and group the nodes. Duplicate the frames fast muter node and change the properties to include the static and dynamic groups. Also, change the properties of the model node to include the dynamic range groups for SDXL, SD3. For SD3, if you are short on VRAM, add the VAE save node and save the SD3 medium VAE. I will show you how to use that in a bit. There is no need to automate the batch size or context, as there are standard values. I recommend a maximum batch size of 4 and an optimal value of 2. The minimum and optimal context should always be 1, and the max should be set at 128. Once you have the workflow set up, it is extremely easy to create multiple TensorRT optimized engines. Let's do one for the Juggernaut X checkpoint. Enable dynamic SDXL high range in the control center. Type in the desired file name. You can add a single LoRa to the checkpoint. I am not sure if multiple LoRas work. Once you set this LoRa strength here, it will be standard. You won't be able to change the LoRa strength later on. Officially, LoRa is not supported. However, this cheese-in method works, as I have tried and tested it. Let's hit the Q prompt and test. Ignore the trace warning. I am on PyTorch 2.4. However, you should have no issues with the default 2.3 version. Ensure that ComfyUI is updated. So, basically, from the load checkpoint node, you only need to disconnect the model. You need to use the clip and VAE from the load checkpoint. I have added a switch from the impact pack to switch between the normal and tensor optimized checkpoint. The TensorRT optimized engine file names are self-explanatory. The $dyn stands for dynamic and stat stands for static. All the parameters are given in the file name itself. Coming to SD3, it can be VRAM heavy. First, ensure the model type is the same as the engine used. Since we use a separate triple clip node, do not load the whole checkpoint. Just add a load VAE node and load only the VAE file, which should be about 160 megabytes. And that's about it. I hope the video was helpful and you learned something new in ComfyUI. Until next time.